Welcome back to Math 574, Finite Element Methods. This is class number 11. We're deep in the heart of talking about the reference triangle, the affine mapping, the canonical affine mapping from the reference triangle into arbitrary triangles, and also, well, actually, I got a little bit ahead of myself. That's what we'll be talking about today. Right now, we've been talking, or lately we've been talking about assembling the global stiffness matrix from the local stiffness matrices. This idea of the reference triangle and the canonical affine mapping that we're going to talk about today is going to be a way of efficiently computing the elements of the local stiffness matrices. Um, in um, well, it's so if you remember the T matrix that I gave you last time, talking about the local to global node numbering and keeping track of that. So utilizing that technology, the reference triangle and this canonical affine transformation that we're going to introduce is going to help us in a big way to efficiently and systematically compute the entries of the local stiffness matrices, which then can be added into the global stiffness matrix in order to do what's the process known as assembly. But in any case, we'll get into all that. Before I move on, though, I wanted to bring up an example that I talked about briefly, very briefly, in class number 10, and that is an example where we've got a global stiffness matrix entry, and we're trying to see exactly how the local stiffness matrices or entries of the local stiffness matrices contribute to that entry in the global stiffness matrix. So suppose we're dealing with a simple case of piecewise linears. So that's R equals 1. And we're going to consider the following mesh in 2D. So we're looking at mainly two triangles in this mesh, but what I want you to think about when you see this mesh is that these two green triangles are far into the interior of the triangulation. It's not near the boundary. Okay, so they're deep in the interior of the mesh. And the reason I'm doing that is because I don't want any one of these nodes, which are touching these green triangles, to be boundary nodes. Suppose we want to calculate the the entry of the global stiffness matrix in row 25 and column 18. And of course, we know that that's the same as the entry in row 18 and column 25 because of the symmetry of the stiffness matrix. So we want to compute this entry. By definition, that's equal to this integral. Integral over the whole of omega, the gradient of phi 18, that's basis function number 18, which means that it's the Lagrange nodal basis that is 1 at node 18 and it's 0 at every other node. And dotted with the gradient of phi 25, which has a similar meaning. Now, the only contribution to this integration is for those triangles, or let's be even more general, it's going to be over that part of the domain that is precisely equal to the intersection of the supports for the 18th and the 25th element. So S18 intersect S25. And I think you can see why that's happening up above. The reason is because if I have element 25 here, outside and element 18 here, so outside of their supports, the functions are identically 0. So their gradients are going to be identically 0. So there's nothing going to contribute that is going to contribute to the integral outside of the intersections of the supports. Now, what exactly is the intersection of the support for element or for basis number 18 and basis number 25? Well, that's precisely equal to the closure of K14 and the closure of K16. Remember, by our convention, we decided that triangles are open sets. Now, why then am I integrating over these open sets rather than the closed sets? The reason is because the integral on that one-dimensional line doesn't add anything to this area integral. Okay, so the integral over the line doesn't add anything. We can delete points and sets of measure zero, and it doesn't change anything. Right. So that means that we've got to compute these two integrations. The integration over K14 of gradient phi 18 dot gradient phi 25 and the integration over K16 of the same. Now notice that within these two triangles, the local node numbering always goes in the counterclockwise order. Global node numbering can be all over the map. It doesn't have to make sense at all. But local node numbering is very specific and very important. Now, which node is node 1 is kind of up to you to decide. It's arbitrary. It just has to be one of the vertices. So once I pick one of the vertices to be node 1, then node 2 is always in the counterclockwise direction from node 1, and 3 same, and then getting back to 1, I'm going still further in the counterclockwise direction. So I've indicated my local node numbers 1, 2, and 3 in triangle 14 as such. In triangle 16, again, it's kind of arbitrary which vertex is going to be node number 1. You simply figure it out. And once you pick that, then node number 2 is in the counterclockwise direction, 3 is in the counterclockwise direction, and getting back to 1 is in the counterclockwise direction. Now, to each one of these local nodes, we have assigned a global node, right? So to local node number 1, we assign, or that's identified with global node 17. Local node number 2 is identified or is mapped to global node 18, and 3 is global node 25. For triangle 16, it can be different. So whereas in triangle 14, node number 18 was the second local node, it's the first local node in triangle K16. 26 is the second local node, and global node 25 is the third. So when we calculate these two integrals, we can resolve them to what we called the local basis functions for each triangle. So let's look at this integral right here. Gradient phi 18 dotted with gradient phi 25. What is phi 18 with respect to K14? So 18 is here. It's actually phi 18 is going to be that part, at least on K14. It's just going to be the local Lagrange nodal basis function number 2. That's called psi 2. And that's because the local node number is 2 there. What about for 25? For 25 on K14, that's this node here. And so it's corresponding to the local Lagrange nodal basis function psi 3 because of this number 3. Now going to K16, see if I can get everything on 1. So going to K16, 18 is going to be the local node number 1. So this local node number 1, or let's say this local node number 3, or local Lagrange nodal basis function, is not the same as this number 3. Okay, they're different. Really, what it should be is we should say, with respect to triangle 16, with respect to triangle 16, and with respect to 14 and 14, right? Really, that's what's going on. They mean different things in different triangles. Okay, so now what I've done is I've resolved these global calculation, or this kind of massive global calculation, to two local calculations. Now remember that this is stored in the local stiffness matrix for triangle 14. And this is precisely equal to A3214, right? A3214. And this guy is exactly equal to that integral. It's A3116, A3116. So both of these entries come from the local stiffness matrix. They add together to compute or to calculate the global entry A2518. So remember, our algorithm for assembling the stiffness matrix is to roam over all the triangles. So when we roam over all the triangles, we're going to roam or hit triangle 14 first. And as we do that, we're going to put all the entries of the local stiffness matrix into their appropriate box or their appropriate contribution in the global stiffness matrix. So we're going to add this guy into the global stiffness matrix for this entry first. And then once we make it to triangle 16, we're going to add this guy in because 16 comes after 14 and we're looping over nodes in order. I hope that makes sense. So it doesn't matter when we calculate the entries of the global stiffness matrix, it doesn't matter if we index over the nodes or we index over triangles, we're going to get the entries in there regardless. It just so happens that it's much more efficient and well understood to assemble the global stiffness matrix via these local stiffness matrices by indexing over and looping over the triangles first. That's how it's done in practice. Okay, so I want to talk a little bit more about the theory of Lagrange nodal basis functions. What is the meaning of these psi functions and how they work and what are their properties? And after that, we're going to get into the discussion that I alluded to earlier about the reference triangle and the canonical affine mapping from the reference triangle. Okay, so to discuss the theory that we need a little kind of lemma that works in 1D, and we're going to use this over and over again in 2D. And then once we know the information about 2D, then we could use that information in 3D and so on. So here's the statement of the result. Suppose that I have an interval, and it's a non-trivial interval, AB in the real line. And suppose that P is a polynomial of degree at most R on that line, okay? And suppose that between A and B, there are these points x1 up to xr plus 1. x1 could be equal to A and xr plus 1 could be equal to B, but otherwise they go in ascending order. x1 is strictly less than x2, which is strictly less than x3, etc. Then P is identically equal to 0 on this interval if and only if P is equal to 0 at each one of these r plus 1 distinct points, right? Each one of these have to be distinct because of this ordering that I placed on these this sequence of points. So P is identically equal to 0 on I if and only if P is equal to 0 at each one of these r plus 1 distinct points xi, I between 1 and r plus 1. All right, so let's go the obvious direction. Suppose that P is identically equal to 0. Well, if P is identically equal to 0, no matter what or how many points we evaluate it at, it's always going to yield 0, right? So if P is identically equal to 0, any points that we evaluate the polynomial at is going to yield 0. The harder direction is the other direction. Suppose that P is, or start here, suppose that we're going this direction. Suppose that P at x1 is equal to 0. Well, P is a polynomial of degree at most R, right? So if P of x at x1 is equal to 0, then P can be written as, and this is just what we understand as the process of factoring. P is now equal to the factor x minus x1, because it's a root, times P1x. But what is P1x? P1x is another polynomial. There's no way it could be anything other than a polynomial. It has to be a polynomial. So P1 has to be a polynomial of degree at most r minus 1. It can't be a polynomial of degree greater or equal to r, because that would contradict our assumption about the degree of P. Okay, so now the next assumption is that, well, let's suppose that P has to be equal to 0 at x2, and then x3, and so on. Well, if it's 0 at x2, then x minus x2 is going to be a root of P, and therefore P is the product of two factors times a polynomial of degree blah, 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 right? And so I can continue from what I started up at the beginning here, and continuing in this way and taking into consideration all of these factors or all of these zeros. I can write P of x as equal to the factor x minus x1, x minus x2, the product, right? X minus xr times prx. For some pr, which is a polynomial, now, because I keep reducing the order of the polynomial, this one is now a polynomial of degree at most 0. So it's a constant. Now, that's if we take into consideration that we have these r factors. So p is equal to this polynomial. But we still have one more factor to take into consideration, right? Or we have one more zero that we haven't accounted for. And that is xr plus 1. So let's plug in xr plus 1. That has to be a 0 by assumption. And of course, now each one of the factors in our decomposition up here is positive, right? xr plus 1 is always greater than x1. It's always greater than x2. It's always greater than x3, all the way up to xr. xr plus 1 is always greater than xr because of this assumption here. So each one of these factors is strictly greater than 0. The only other possibility is that c is itself equal to 0 because of this. I have a product of positive numbers, so that product is positive, times a constant must equal to 0. A positive number times a constant is equal to 0. So the only possibility is that constant is equal to 0. But now I can put the 0 in for this factorization, and that tells me that P is identically equal to 0 on all of I. So that's the proof. And think about what it says. It makes sense, right? So if P is a polynomial of degree at most r, but we discover that it is 0 at r plus 1 points, then it must be that it's just equal to the 0 polynomial. Okay, it's a little bit, well, let's think about it from this point of view. If a quadratic polynomial is found to have three distinct zeros, three places, three distinct points where it's equal to 0, then it has to be true that that polynomial is just equal to the 0 polynomial. And you can extrapolate further. Let V be a polynomial of degree 1 over a triangle K that is not degenerate. So a non-degenerate triangle is any triangle that has interior area. A degenerate triangle is one where basically it's not a triangle at all. It's essentially a line. Then V is uniquely determined by the 3 degrees of freedom, Vaj, j equals 1, 2, and 3. In other words, V is uniquely determined by its 3 values at the vertices. Think about it like this. So if this was a one-dimensional example, and I said, I have a line over an interval, right? Let's say over the interval AB. And I have a polynomial of degree at most 1 that's a line, right? What do we know about that? We know that that polynomial is uniquely determined by its two endpoints, A and B. And that's, that's all there is to it. Now, the analog of this in 2 dimensions is that if I have a triangle, which is non-degenerate, then that polynomial of degree 1, which sits atop of that triangle, is uniquely determined by its values at the at all the 3 vertices, at the 3 vertices A1, 2, and 3. Okay, remember this is my notation for the vertices of the triangles. So how can we prove this? Well, there's a bit more to it before I get, okay. One more part of the theorem that I forgot to state before we talk about the proof. Furthermore, we can decompose V as using those 3 degrees of freedom. And it's very simple. V can be written as the sum, I from 1 to 3, V evaluated at the 3 nodal points, A1, A2, A3, times the corresponding local Lagrange nodal basis function, psi1, psi2, psi3. If this is true, then it only takes one more step to show this is the linear, not linear independence. This is the spanning property for bases. There's only one more little step to show that B1, the collection of these 3 elements, these local Lagrange nodal basis functions, is a basis, but it's only a basis for that local polynomial space P1 over K. So how would I show that that's the case? How would I show that this is the case? Well, the first thing is I want to show that if I have a polynomial of degree 1 and I have this decomposition, okay, or let's say this decomposition right here, what I want to show is that this decomposition actually is equal to that. And how could I do that? I could subtract the 2 and show that that's a polynomial of, well, that's a polynomial of degree 1, which is 0 at 3 distinct points. Well, I want to use what I learned in 1 dimension to show that that's actually just going to be equal to the 0 polynomial. So that's the way I do it. So I'm going to leave that as an exercise to you. And suppose now that we have the case where we have a polynomial of degree 2 over a triangle. Then that polynomial is uniquely determined by 6 degrees of freedom. Now, it doesn't matter which 6 degrees of freedom I choose, but I'm going to choose them in a very specific way. I'm going to choose them as A1 through A6. And if you remember from last time, what that means is for our triangle, didn't do that right. So there's our triangle. So if that's A1, A2, A3, we agreed that A4 is going to be here. A5 is there. That's the edge midpoint for that side. And finally, A6 is here, the edge midpoint for that side. So these 6 degrees of freedom uniquely determine the polynomial. In other words, I can write this in a basis expansion where the coefficients of that basis expansion are precisely the values of the polynomial at these 6 points. And that means that I have the spanning property for those local Lagrange nodal basis functions, which we talked about last time, psi1 through psi6. And one more step further tells you that you have linear independence of all these basis functions. And if I have spanning property and linear independence, then B2 turns out to be a basis for P2K. So how can I prove this? Okay, so I told you the basic idea for proving this, and now I'm going to show you exactly how it's done in 2D. All right, so we're first going to observe without proof that the dimensions of P2 over K is exactly equal to 6. It's not hard to see this, and it's because I can write 6 basis elements. 1, x, y, xy, x squared, and y squared. So this is a 0th order polynomial, first order polynomials, second order polynomials. There are 3 of those. And therefore, I can show that each one of these is a linear independent and spans the whole set. And therefore, this is a basis for P2K. All right. But all I really care about is the fact that the dimension of P2 is equal to 6. All right. Now, it works out, and for a reason I explained above, if V is a polynomial of degree K, and we find that V is equal to 0 at 6 distinct points, well, specifically these 6 distinct points, then V is going to have to be exactly equal to 0. So let me say that again. If V is a polynomial of degree 2 that has the property that at the 6 vertices, well, at the 3 vertices plus the 3 edge midpoint nodes, it's equal to 0, then V must be identically equal to 0 from that polynomial space. Okay, so this is what I want to prove. I'm going to introduce some definitions. Sigma 3 is going to be the side opposite of the vertex 3. Sigma 1 is going to be the side opposite of vertex 1, and sigma 2 the side opposite of the second vertex. So let's suppose that V is equal to 0 at the 3 nodes A2, A5, and A3. So A2, A5, and A3. What happens if it's 0 along that line, or at those 3 points? Well, if I restrict a polynomial of degree 2 in 2 space dimensions to a line, that gives me a polynomial of degree 2 in 1 dimension. Okay, so what I'm saying is, if I restrict that 2-dimensional polynomial in 2 variables, to a line, in this case, a sigma 1 line, that's a polynomial of degree 2, and it's over some finite interval. I don't know what the interval is, but I can say that it's a polynomial in 1 variable, which is what I mean here. Now, it must be true that V, when I restrict to sigma 1, is identically equal to 0 on sigma 1. Why? Because of the result that we stated and proved earlier, because of this result. It's a polynomial of degree 2 over a line over an interval that's 0 at 3 distinct points. So that must mean, because of this, that that polynomial is identically equal to 0. So that's the first fact that I'm going to put in my pocket. When I restrict to these 3 points, I have a second degree polynomial. I notice that I have zeros at 3 distinct points, and therefore the polynomial restricted to that interval or that line has to be equal to the 0 polynomial. Now, what I'm claiming is, what that means is that V, remember it's a second degree polynomial, it must be equal to the factor lambda 1. Remember the barycentric coordinates that I introduced last time. Lambda 1. Let's remind ourselves what lambda 1 is. Lambda 1 is 0 along that line. It's equal to a half along that line. It's equal to 3/4 along that line. And finally, it's equal to 1 at that point. let's review. So 0, lambda 1 is a half, or not a half, but a quarter. It's a half, 3/4, and 1. And then, of course, all values in between. That's lambda 1, the barycentric coordinate. So by the same logic that I had before, if it's 0 along that line, lambda 1 must be equal to a factor. Okay, lambda 1 must be equal to a factor, or must be one of the factors. Okay, but what about this polynomial, this remainder polynomial? It has to be a polynomial of degree 1. And I have a typo there. It has to be a polynomial of degree 1. That's the so-called remainder. So this guy is the factor, and that is the remainder, right? And so now we want to argue that, well,
Sorry?
go ahead.
Caroline, see the FB, or does that stand for something else?
Or this is a Nashville soccer team.
Okay, so,
Oh,
Yeah.
Jack, can you hear me?
sorry, I'm ignorant of both.
Oh, you're totally fine. I think they're pretty.
Jack was not muted. Okay, now he is. Okay. Now what we want to argue is that this remainder is actually has a factor which is just exactly equal to 0. All right, so now by a similar argument, we can argue that V is identically equal to 0 on sigma 3, right? Because when I restrict to sigma 3, it's a polynomial of degree 2, and it's 0 at 3 distinct points. Therefore, it has to be that it's identically equal to 0 on this whole line. So when I restrict to sigma 3, it's identically equal to 0. But notice that one of its factors, lambda 1, is equal to 0 for x in sigma 3 only if and only if, x is equal to a2. So the only way that lambda 1 can be equal to 0 is at that point. So there's no other way that this guy can contribute or give rise to the fact that we have this polynomial being 0 on sigma 3. It must be that W1 has a factor which is exactly equal to lambda 3. Lambda 3 equal to 0 is here. Remember, lambda 3 is 0, lambda 3 is a quarter, lambda 3 is a half, 3/4, and 1, and all the values in between. It must be that W1 can be written as the factor lambda 3 times a remainder polynomial W0. But what do we know about W0? W0 must be a remainder, which is a polynomial of 1 degree less. So a polynomial of degree at most 0. So that means now we've resolved V as C, lambda 1, lambda 3. Okay, for some constant. Now finally, what do we know? We know that we've used the zeros at these these 5 points. We haven't used the fact that it's 0 at this point yet. So let's now finish it up by evaluating at V at the node A6. If I do that, then I have to get 0 because I've assumed that V is equal to 0 at all 6 of these points. I'm trying to show that if V is equal to 0 at all 6 nodes, then V must be identically equal to 0. Now, the reason why this is sufficient to prove everything else that I want to prove is left to use an exercise. Okay, I didn't prove that part. We started with the assumption that if we can show that a polynomial which is a degree 2 and equal to 0 at the 6 nodes is identically equal to 0, then we've proved all that we need to prove. So that's our starting point. In any case, now that I'm evaluating at A6, what do I get? I get 0. But if I plug A6 into this side of the polynomial, what is the value of lambda 1 at A6? Remember, lambda 1 is going to be 0, a quarter, 1/2, 3/4, 1. It's going to be equal to a half all along that line. So if I insert A6, that's just going to be a half. By the same logic, when I insert A6 into lambda 3 is equal to 0 there, a quarter, 1/2, 3/4, and 1. It's equal to 1/2 at A6. So at A6, I get a half. I get 1/2 times a half. So ultimately, I have 0 is equal to 1/4 times C. The only possibility is that C is equal to 0. And therefore, I've just shown that V is identically equal to 0 on all of K. Okay? So I suggest we did the harder of the two. If you go back now, you should be easily able to see how or why this works. Now, the missing piece here again is that um, we said that all we need to show is that if we have this implies that, then that shows that these two facts are true. Okay, so I leave it to you to show that. In fact, what we're doing is we're proving the stronger statement that this is actually a basis. All right. So the next topic I want to talk about is something that I mentioned at the very beginning. I falsely said or incorrectly said that we had talked about this previously, and that's just because it was kind of on my brain for the past few days. We want to talk about the topic of affine mappings of triangles. Now, I want to think about a mesh as being composed of, let's say, millions of triangles, right? Many, many triangles which compose the mesh. And we know that there aren't any hanging nodes, and we know that there aren't any degenerate triangles. So what I can think of is each triangle has a certain sort of nature to it, right? If I look at a triangle in the mesh, let's say like this, I'm really kind of zooming in on this triangle because the way I should think about this is that each triangle is pretty small in diameter, right? It's if I have millions and millions of triangles, let's say of the domain 0, 1 cross 0, 1, then probably most of my triangles are very, very tiny in size. That means its longest edge is pretty small. So this is a zoom in. I'm zooming in here. All right, so now we've zoomed in there, fair enough. What I want to think about is for each triangle is small. For each triangle, I'm going to think about making a mapping from a triangle which is not necessarily small. In particular, I'm going to think about mapping the so-called reference triangle. So my lots of people take different reference triangles. Some use equilateral triangles. I'm using this isosceles triangle. That has the vertices 0, 0, 1, 0, and 0, 1. I'm going to call that reference triangle K hat, and I'm going to think about a mapping which takes K hat into K in such a way that it preserves a couple of things. One of the things I want to preserve is maybe I've got this counterclockwise numbering of nodes, right? Just as I've always had. I want to preserve under my mapping that I have, I want to preserve that counterclockwise ordering, which is, there's no ambiguity here because I'm mapping a 2D triangle to a 2D triangle. What else might I want to do? Well, I want to map an edge to, a straight line edge to another straight line edge, right? And well, in fact, each one of the straight line edges should be mapped to straight line edges. What else should I want to do? Um, that's the most important things. If I have a really crazy mapping, of course, then if I map it under some transformation, then it might not even end up being a triangle. It could map triangle into a circle or something like that. All right, now I want to consider very specific mappings which do this, and it maps all in such a way as they map all the points from k hat into k that preserves the things that I said already. And in fact, this mapping is one-to-one and onto, and also affine. It turns out I can do all of these things if I take the mapping to be of this form. Okay, so if I want to map a point x vector x hat, then I multiply by a matrix bk. In fact, I do 2 by 2 matrix times this 2 vector, and then I'm going to add a vector, add a shift vector. Okay, and as I said before, I want to do this in such a way as that I map aj hat into aj, j equals 1, 2, and 3. Well, it's not hard to show that if I pick my matrix bk to be this matrix here, and my shift vector to be a1, then I precisely get 11.1. That is, I precisely get this. Okay, so I'm going to leave it as an exercise for you, a very, very easy exercise to show that if I pick BK to be this 2 by 2 matrix, and if I pick my shift vector to be this vector, then I precisely get this, this preservation. I get a lot more properties as well. In fact, what you can show is that not only do you preserve these points, but the object that you're going to, so I'm taking this as my domain and this is my range. You can show that the range is exactly a triangle. All right. So our first, I'm gonna state a lot of properties which are elementary in nature, but do require that you go through and check some of these facts. Not hard, but I would say tedious. So the first thing I want to say is that the matrix BK is invertible, and its inverse is, well, it's the usual 2 by 2 inverse. You swap the diagonal elements. Let me see if I get that right. I'm going to swap the diagonal elements, and then I'm going to negate the off diagonal elements and divide by the determinant. So it's invertible as long as that triangle into which I'm mapping K is not degenerate. Notice that my BK is entirely determined, or I should say BK is entirely determined by the points in my triangle K, right? So, for example, A21, what does that mean? What is A21? Well, that's the second node, first coordinate, according to this prescription. So the second node, A2, and the first coordinate is what I mean when I say A21. So these are just the coordinates of the nodes from my reference, or not reference triangle, but the target triangle. That's what tells you how you should pick the elements of the BK transformation. So as long as the triangle into which I'm mapping is not degenerate, then this determinant is going to be non-zero. That's what it means, or that's how we know that 2 by 2 matrix, or any matrix actually, is going to be invertible. So as long as K is non-degenerate, then my determinant is not going to be equal to 0. Now a determinant, or it ends up, it can be shown that, and part of the proposition here is that the determinant of BK is precisely equal to twice the area of the triangle. So it makes sense. If the triangle is non-degenerate, that means it's got positive interior area, or positive area. And so K is not, the absolute value of K is, well, not absolute value of K, what am I saying? This is the measure, the two-dimensional measure of K, is strictly positive. and therefore the determinant, if this formula holds, is greater than 0. So the only real difficulty is showing that this formula holds. Okay, so I leave that as an exercise for you. Because once I know that this holds, then if the triangle is non-degenerate, the determinant is strictly positive, and therefore my inverse formula holds. And I guess it's not exactly part of the statement here, but it's not hard to show that this mapping is also going to be one-to-one and onto triangle K hat onto K, one-to-one onto. Okay, so I leave that as an exercise. Now, why am I wasting any of your time talking about this reference triangle? Well, the reason is that it provides a very useful mechanism for computing integrals of the following form. If I want to compute an integral of some function over a triangle, then it turns out if I know how to represent that triangle through an affine mapping, it's a lot easier to do this integral calculation over the reference triangle. And similarly, if I want to compute something like this, a gradient of f dot gradient, or I'd say the integral over k of gradient f dot gradient g, f and g are just two C1 functions, say, then a nice easy way to do this is use the technique of the reference triangle. All I need to know is what is the canonical mapping fk one-to-one onto k. So I really just need to figure out what this guy is. And if I know that, then computing these integrals is going to be a kind of snap. All right, so we want to now know how does knowing information about this reference triangle mapping and this canonical affine mapping from a reference triangle into a triangle K, how is this useful? So let's consider the next theorem. Suppose that G is a C1 mapping from R hat into R. And suppose that it's one-to-one onto from this bounded closed set to this bounded closed set. Assume that R is Riemann integrable. What does it mean for a region to be Riemann integrable? Well, it means I can break it up into boxes, or I can break it up into rectangles, the usual way that we do in Riemann integration, and I can get a value. So it's a domain that's not so unpleasant. Um, we could take mappings from Lebesgue measurable sets into Lebesgue measurable sets, but that's um, that's quite a lot more difficulty than we actually need. So what do you want to think about here? Just think about something simple like a rectangle. Okay. All right. So now let's write x equals to g of x bar, or x hat, where x hat is anything in r hat. Okay, so in other words, what I'm thinking about doing is transforming my coordinates x hat into coordinates x. So this is kind of a coordinate transformation. And I'm thinking about, basically, I have a starting region over here in space. Think about it as something like this. Let's just do something simple. So we have one copy of space. And we're going to call this r hat. And this guy is r. So points x hat get mapped to points x under this G mapping. Okay. Next, suppose that f is a function that takes points of this rectangle R. So I think about f as being a function of this regular variable x, and maps them into the real numbers. And suppose that f is just a continuous function. This mapping here is 1-to-1 onto and also C1. Then, if I want to integrate f over this region R in its native variable x, then that's exactly the same as, or that's equal to, an integral over the region R hat of f composed with the mapping G times the determinant of something called the Jacobian matrix. So what's the Jacobian matrix? The Jacobian matrix is the Jacobian matrix for that mapping G. It's just going to be the derivative of G1 with respect to x hat 1, etc. So this is the standard um, integral transformation theorem that you saw from Calculus 3 way back many years ago. Okay. And all we're doing here is transforming our space the way that you did it back in Calc 3 or Calc 2, wherever you saw this theorem. The way you used this theorem was maybe you would have a really ugly, maybe you had a really ugly region of space that you were doing the integration over, and you wanted to transform that to a simpler region. That's usually how it worked. So, for example, the way we should think about this region R hat is it's just a simple square and much easier to integrate over. So what I really want to do is I have this integral. I want to know what is this, the value of that. I'm going to actually transform it or move it to an integration over R hat, which is a lot simpler. And the penalty for doing that is that, well, I've got to do a composition of functions and I've got to carry around this Jacobian. Okay. So I'm not going to prove that. That's something that you saw from Calc 2 or Calc 3. Now, how are we going to use this in the context that we have before us? We're going to use this precisely because what we really want to do is compute integrals over what? Not the reference triangle, but the arbitrary triangle K. And we want to move those back to the reference triangle K hat. So that's how we're going to use these. And we're going to use, of course, the simplest transformation from K hat into K, the canonical affine mapping. So suppose that FK is that affine mapping from above, which takes the reference triangle into our triangle of the mesh. And suppose that K is not degenerate, then if F is a continuous function, which takes points from the triangle into the real numbers. So this is a real valued function over the triangle K in the mesh. Then the integral over that function over the triangle K in the mesh is exactly equal to this integral. And all we're doing is applying this theorem here. This is the hard integral, and this is the integral that should be a lot easier for us to do. What about this? Where did this come from? This came from the fact that we can actually easily compute the Jacobian of this transformation. The Jacobian of that transformation just works out to be precisely 2 times the area of the triangle K. So if I take the determinant of the Jacobian map, it's just exactly equal to twice, which by the way is the same as the determinant of that transformation matrix BK. So that probably plays a role in this proving this theorem. So this is the Jacobian. And since it's independent of the point values, normally this is not independent of point values, but in our case, it's going to be. Since it's independent of the point values, it simply comes out front of the triangle. So this is a very, very simple corollary of this powerful region transformation integration formula. Okay, suppose that psi I in the what would this normally be? This would just be the ith local Lagrange nodal basis function on the triangle K. And suppose that psi I hat is the corresponding one. Here's a typo here. That should be K hat. Is the corresponding local Lagrange nodal basis function on the reference triangle for I equals 1 up to D. So if R is equal to 1 piecewise linears, then D is going to precisely be 3. And if R is equal to 2, then D is precisely going to be equal to 6. It follows this formula. But interestingly, this formula holds true for polynomials of degree 3 and 4. So R equals 3 and R equals 4 and 5 and so on. Okay, so this formula holds true, even though we've only discussed it and shown it is true for R equals 1 and 2. Okay, so these are our local Lagrange nodal basis functions on the triangle and on the reference triangle, respectively. And suppose that F is the standard, F sub K is the canonical affine mapping from K hat into K. Then psi I hat is equal to psi I under this transformation. Okay, so what is this saying? I guess the easiest way to look at it is, well, we know what these guys look like on the triangle K. How could I find the corresponding basis element on the reference triangle? Well, I simply compose that guy with this function, this affine mapping, which of course takes points from the reference triangle into points on the triangle K. Again, if I do this composition, then I precisely get back to the basis function psi I hat, the one that corresponds to this guy, but in the reference triangle. Now, how can you show this? The easiest way to show this is, remember that we had formula for psi I for any arbitrary triangle in terms of barycentric coordinates. I can also come up with a version of those local Lagrange nodal basis function with respect to the barycentric coordinates on the reference triangle. So I know exactly how to write these functions in terms of barycentric products of barycentric coordinates. So go back to the last lecture if you want to see how this is done. We gave the formulas for R equals 1 and R equals 2. Now, then I claim it suffices to simply show that that the barycentric coordinates transform according to the same rule. But there are only 3 of those, so that's a lot easier to show. So I want to show that basically the barycentric coordinate psi I corresponds to the barycentric coordinate psi I hat with respect to or on the reference triangle. And if I can show that, then this transformation is going to be true. So I'm going to leave that as a homework exercise. So instead of having to show, for example, for polynomials of degree 2, instead of having to show 6 different formulas, I really only have to show the 3 basis functions transform according to the way that you would expect. So I'll leave that to you as an exercise. Now, what this also shows is the following. If the basis functions transform into basis functions, then and remember, the basis functions are going to be the building blocks for polynomials, then that means that affine mappings preserve polynomials. So in other words, if I have a polynomial on the reference triangle or on the triangle K, then under the transformation F or F inverse, remember F is an invertible map, gets transformed into a polynomial. Okay, and the reason is because all the polynomials are ultimately constructed using these barycentric coordinates, which get preserved under this transformation. Okay, so this says barycentric coordinates get preserved under the transformation of F, and if that happens, then basis functions gets preserved and affine mappings preserve polynomials. I mean, actually, what we've really shown here is that this affine mapping preserves polynomials, but it turns out that all affine mappings ultimately do preserve polynomials as well. Okay, suppose that we have again our canonical affine mapping from the reference triangle K hat into K. Then if f is a function from K into R, so this is a function on the tiny little triangle in our mesh, and suppose that it's a C1 function, then it follows that the gradient of f in the old coordinates x is equal to the gradient on the reference triangle in the reference triangle coordinates times this matrix, bk minus transpose. In fact, you have to pre-multiply by bk minus transpose. So this is the inverse of the transpose matrix. That's what minus transpose means, the inverse of the transpose matrix. All right, so this just means the gradient in the coordinates of the reference triangle, the hat coordinates. And what do we mean by this part here? F hat, X hat? Well, that's just defined as F composed with the mapping FK, right? So by the way, just so you're clear, right? So this should be clear that that's just equal to that composition. And by composition here, I'm going to mean that I do this operation first, and then finally I do F. That's what we mean by this function here. Ultimately, I get a new function, which is a function of the coordinates in the reference triangle. So let's prove this. So the easiest way to do this is let's just start off by doing this calculation and figuring out what the heck it means. So if I want to compute the gradient in the reference triangle coordinates of this thing f hat, what am I doing? I'm taking the derivatives with respect to the hat coordinates of f hat. So let's take an arbitrary reference coordinate. It's going to be hat I. So I is going to be 1 and 2. Okay, so take the derivative d by d x hat I of f hat. So that's just by definition exactly equal to that. This is my original f, and f is a function of two variables, and this guy was defined as the composition of f and f k. So now to take this derivative, all I'm going to do is apply a chain rule. So I'm going to take the derivative with respect to f's first coordinate. Its natural coordinate are going to be x1 and x2. So take the derivative with respect to the first natural coordinate, x1, but then by chain rule, I have to take the derivative of x1 with respect to hat xi. Take the derivative, you have to add to that the derivative of f with respect to its second natural coordinate, x2, times the derivative of x2 with respect to x hat I. But now, all I want to do to finish this out is to show that, well, really, this calculation here is nothing more than these numbers here. In other words, That's the same. So what I want to show is actually this part here is going to be the element of BK, first row, ith column. And this is the same. So really what I'm saying is I want to show that this guy here is an element of BK in the second row, ith column. Okay, and so that's the calculation that I was doing here. Taking the derivative of this and showing, yeah, and basically showing that that is that calculation there. And that's that guy. Okay. If that's true, then now I know exactly what that is. It's just equal to this. But now I can convert this back into matrix vector multiplications. This just really is equal to a matrix times a vector. These are the components of the gradient of f in its original coordinates. And so I can show that this is the ith coordinate of this, and this is the ith coordinate of that. That's really what I've shown. But I is arbitrary. It could be 1 and 2, and so I have this. Right. So now how do I get the formula that I stated earlier? Well, all I have to do is now take this matrix. It's invertible as long as K is non-degenerate, and I'm going to multiply by its inverse. Remember, the inverse is going to be BK transpose inverse, which comes over here, which is, using our usual notation, BK minus T. Okay, so that gives precisely the formula that I wrote down. Okay, but everything starts with, it's easiest if I simply start with this calculation and use the chain rule. That's all I've done. I've just used the chain rule. Okay, so if I know this piece of information here, and what else do I know? I know this piece of information here. I have all the information I need to know now in order to transform integrals from an arbitrary triangle back to the reference triangle. So I'm going to use this transformation formula, and I'm going to use this bit of information to show that I can transform integrals that look like this to integrals which look like this. In fact, I'm completely done. It's just an application of the last two results. Now, why would I want to compute the integrals of this type? The answer is because these are the elements we showed in the very first slide. These are the elements of the local stiffness matrix, right? Or the local stiffness matrices. And in fact, this one is the JI entry of the local stiffness matrix for triangle K. So, right, this is exactly here. Well, yeah, right? That's exactly what I'm talking about. That's this guy here. So I don't want to do that computation on the small triangle K. I want to move it back to the reference triangle. And if I do that, I now have a nice easy formula for it. So this should be computable. What about these things? Well, these I can store up because I'm going to have my, for my reference triangle, I know what these guys are. They're very easy to express. What about these things? This is just the mappings, and I keep track of it's easy to keep track of these mappings. This is part of the transformation FK, because we said FK was exactly equal to BK plus A1. So I've stored up these guys. they're 2 by 2 matrices. I can easily take the inverse of the transpose of those guys. No problem. I can store up these, I can put them, I can do a pre-processing step and just keep them somewhere, right? So if this is going to be piecewise linear, then each one of these gradients are going to be piecewise constant. If it's piecewise quadratic, then each one of these gradients is going to be piecewise linear. All right, so I can store those values up. When I'm interested in figuring out what this integral is, then I can use my reference triangle to do this calculation quickly and easily. These are stored up and known, so I just do a quick multiplication, and then I do the integration over the reference triangle. Easy peasy. So that's the idea of using the reference triangle in order to calculate the elements for the local stiffness matrix. You always do it this way. You always do it with respect to the reference triangle because it turns out it's much easier than doing these arbitrary these calculations over these arbitrary elements in the matrix. This gives us um, uh, a standard sort of well understood, well defined place to do these area integrals. And I just keep doing them always over the reference triangle using these stored values. Very easy to do, and it's quite straightforward. So what we're going to do next time, that's the end of the lecture. What we're going to do next time is we're going to focus on how now do I practically do these calculations. Knowing, as I just said, this is going to be generically if p is equal to 2, if p is equal to 2, then this is going to be a polynomial of degree 1 times a polynomial of degree 1. So the product is going to be a polynomial of degree 2 in general, whenever we're dealing with r equals 2. So now I've got to quickly and easily integrate polynomials of degree 2. How do I do that? Well, it turns out the easiest way to do it is to use a process known as Gaussian quadrature. So you've probably seen Gaussian quadrature talked about in one space dimension. We're going to talk about Gaussian quadrature in 2 space dimensions over something called the reference triangle. And with that, I will stop the lecture and take your questions.